While you're watching this, 95% of people clicked away already. They saw 1 hour of pure math and ran. But you? You're different. You're about to do something absolutely psycho. Here's what's about to happen. We are going to have 1 hour of intense probability practice, starting now. And trust me, by the end of this journey, you'll look at probability problems completely differently. Final warning, if you're not ready for psycho-level mental focus, if you can't handle 1 hour of concentrated practice, if you want the easy path, close this video now. But if you're ready to be different, if you're ready to be psycho-focused, if you're ready to join the committed few who actually finish this, then you're exactly where you need to be. Problem 1 starts in 3, 2, 1. A coffee shop offers 3 sizes: small, medium, large, and 2 temperatures, hot, iced, for their drinks. What's the complete sample space for all possible orders? When you order, you're making 2 choices: size and temperature. Check out this systematic approach. Let's think about it. Each size can be either hot or iced. That means small gives us 2 options, medium gives us 2 more, and large adds another 2. Here's our complete sample space. 6 total outcomes, every possible combination of size and temperature. Now, let's define the event E equals ordering a medium drink and list its outcomes. So, what exactly is event E? It's any order that involves a medium drink, regardless of temperature. Looking at our sample space, we can quickly spot which outcomes belong to event E. Remember, we only care about the size being medium. So, E equals medium hot, medium iced. Just those 2. What is P of E? Here's that fundamental probability formula. We've got 2 favorable outcomes, the medium drinks, and 6 total outcomes in our sample space. So, what's the probability? We've got 2 favorable outcomes out of 6 total. That gives us 1/3, about 33%. This makes perfect intuitive sense. We have 3 sizes, and medium is just one of them. So, naturally, about 1/3 of all orders should be medium. Here's what's really important. Sample spaces need to contain complete outcomes. Every element has to fully describe what happens in the experiment. You can't just say medium. You need medium hot or medium iced, because both the size and temperature matter. In a survey of 100 students, 65 used Netflix, 45 used Disney+, 30 used both services. What's P of uses Netflix or Disney+? Your instinct says 65 plus 45 equals 110 students. But wait, we only surveyed 100. Something's fishy here. Check out this Venn diagram. The problem is those 30 students who use both services. When you just add 65 plus 45, you're counting them twice. So here's the addition rule for probability. When you want the probability of A or B, you add their individual probabilities but subtract the overlap. Otherwise, you're double counting. So let's crunch the numbers. Netflix users make up 65% of students, Disney Plus users are 45%, and those using both services, 30%. Now, when we apply the addition rule and account for that overlap, we get 80% of students using at least one service. What's P of uses only Netflix? Now, this is where it gets interesting. Look at the Venn diagram with the regions highlighted. Uses Netflix is not the same as uses only Netflix. There's a big difference. To get only Netflix users, you take all Netflix users and subtract those who also use Disney+. So if we take all Netflix users and subtract those who also use Disney+, we get 35% using only Netflix. What's P of uses neither service? Here's a clever trick. Use the complement. If 80% use at least one service, then we know from our calculation that 80% use at least one service, so that leaves 20% using neither service. What's cool about Venn diagrams is they make everything visual. You can literally see the overlaps, which prevents those sneaky double counting errors. Trust me, drawing these will save you from so many mistakes.
You're creating a 4-character password using lowercase letters A through Z. First question. How many passwords are possible if you can repeat letters? This is the multiplication principle. When making sequential choices, multiply the number of options at each step. Think slot by slot. First character, 26 choices. Second character, 26 choices. You can repeat. Third character, 26 choices. Fourth character, 26 choices. When we multiply it all out, we get almost 500,000 passwords, 456,976 to be exact. That's almost 500,000. But what if all letters must be different? Now it's a permutation problem. We're choosing 4 letters from 26, where order matters and no repetition is allowed. Think about it step by step. First character, 26 choices. Second character, 25 choices. Can't reuse the first. Third character, 24 choices. Fourth character, 23 choices. Crunch those numbers, and you get 358,800 passwords. Wow. We lost almost 100,000 possibilities by not allowing repetition. Now, here's the scary part. If a hacker tries 1 password per second, how long to try all those 456,000 passwords we just calculated? 456,976 seconds. Let's convert this. Let's see. That works out to about 7,600 minutes, which is roughly 127 hours, which means just over 5 days. Your 4-letter password? Gone in less than a week. And that's trying manually. Modern computers try millions per second. Your 4-letter password? Gone in milliseconds. So, here's what matters. Anytime you're making sequential choices, ask yourself, can I repeat? Does order matter? These 2 questions unlock every counting problem you'll ever face.
Historical data shows 20% of days are rainy. On rainy days, 80% are cloudy. On non-rainy days, 30% are cloudy. You wake up and see it's cloudy. What's the probability it will rain today? This is conditional probability in action. We have evidence, cloudy sky, and we need to update our belief about rain. Your instinct probably says it's cloudy and 80% of rainy days are cloudy, so there's an 80% chance of rain. Wrong. This is backwards reasoning. Let me show you why. Let's think about 100 days. 20 days are rainy, 20%. 80 days are not rainy, 80%. Now, of those rainy days, 16 days are cloudy, 80% of 20. 4 days are not cloudy. Of the non-rainy days, 24 days are cloudy, 30% of 80. 56 days are not cloudy. Total cloudy days, 16 plus 24 equals 40 days. So if you see clouds, you're in one of those 40 days, but only 16 of them are rainy. Now we can use Bayes' rule. This formula lets us flip conditional probabilities, going from P of B given A to P of A given B. Now let's work through this step by step. We know from the problem that 20% of days are rainy and 80% of rainy days are cloudy. To find the total probability of cloudy days, we need to consider both paths, rainy days that are cloudy plus non-rainy days that are cloudy. When we calculate both scenarios and add them up, we get 40% of all days are cloudy. So what's the actual probability of rain given we see clouds? When we use Bayes' rule with the numbers we just calculated, we get 40%. Only 40% chance of rain, not 80%. Here's what's mind-blowing. The clouds are actually evidence against rain. Why? Because clouds are so common on non-rainy days that seeing clouds doesn't strongly indicate rain. This is why conditional probability is so powerful. It forces us to think about all the ways something can happen, not just the obvious ones.
A factory has two production lines. Line A, 95% success rate. Line B, 98% success rate. The lines operate independently. What's the probability both lines produce a good item? This is about independence. Since the lines are independent, we can use the multiplication rule for independent events. Since the lines are independent, we just multiply their success rates. That gives us 93.1% chance both lines work perfectly. What about the probability at least one line produces a good item? Here's the smart way. Use the complement. For at least one problems, it's often easier to calculate the probability of none occurring than subtract from one. For at least one good item, let's flip this around. The chance both lines fail is incredibly tiny, just 0.1%. So the probability at least one line succeeds, 99.9%. Almost guaranteed success. So what's the big deal about independence? It means one event doesn't change the probability of another. When events are independent, just multiply their probabilities. It's that simple. No complicated formulas, no conditional thinking, just straight multiplication. All right, let's talk about something we all do, ordering food delivery. A delivery app charges a $2 base fee plus $1 for every mile traveled. And here's the thing, the distance varies uniformly between 1 and 5 miles. You never know if you get the place right around the corner or the one across town. Let X equal total charge for a random delivery. So what values can X take? This is where we transform a real-world situation into mathematical language. We're turning this random process, those varying distances, into numbers we can actually work with. Think about it. The total charge is always $2 base fee plus $1 times whatever distance we travel. So, if we get the closest delivery at just 1 mile, that's $2 plus $1, giving us $3 minimum. And if we get unlucky with a 5-mile trip, that's $2 plus $5, making $7 maximum. But wait, here's what makes this interesting. The distance is continuous. We're not just talking about 1 mile, 2 miles, 3 miles, no. The delivery could be 1.5 miles, 3.7 miles, 4.999 miles, literally any value between 1 and 5. So X can be $3, $3.50, $4.73, $6.99, basically any amount between $3 and $7. Mathematically, we say X takes values in the interval from $3 to $7. Now, what's the expected value of X? In other words, if you order food 1,000 times, what's the average you'll pay? Here's something beautiful about uniform distributions. The expected value is simply the midpoint. Since distance is uniform between 1 and 5 miles, on average, you'll travel 3 miles, right in the middle. So the expected charge is $2 base plus $1 times 3 miles average distance. That gives us $5 on average per delivery. Simple as that. Now here's where it gets interesting. The app assigns you 20 deliveries randomly, all independent trips. What's your expected total earnings for the day?
Since each delivery is independent, we just multiply. 20 deliveries times $5 average per delivery equals $100 expected earnings. Not bad for a day's work.
But wait, plot twist. The app actually uses a balancing algorithm. If you just had a long 5-mile delivery, they'll give you a short one next. And if you had a short trip, the next one will be longer. The deliveries are clearly not independent anymore. So what happens to your expected earnings now?
Here's the mind-blowing part. It doesn't matter. Your expected earnings are still exactly $100. See, even though the deliveries are now dependent on each other, each individual delivery still has the same expected distance of 3 miles. The balancing might change how the distances are distributed, but it doesn't change the average. This is the magic of linearity of expectation. It works regardless of whether events are independent or not. So here's what we learned. Random variables let us turn messy real-world scenarios into clean math. And expected value? That's your long-run average. Individual days might vary wildly, but over time, it all averages out to that magical number.
Okay, picture this. We're at the movies, and I surveyed 200 customers about their snack choices. This is where data gets really interesting. Check out this table. We've got adults and children on the rows, and their snack choices, popcorn, candy, and soda, on the columns. Each number tells us exactly how many people fell into each category. It's like a treasure map of movie snack preferences. First question, what's the probability someone is both an adult and bought popcorn? This is what we call joint probability. We want both things to be true at the same time. They're an adult, and they chose popcorn. Look where the adult row meets the popcorn column. 40 customers. Out of our 200 total, that gives us 20%. 1 in 5 customers are popcorn-loving adults. Now, what if I just ask, what's the probability any customer bought candy? Doesn't matter if they're adult or child. This is marginal probability, and here's why it's called that. Look at the margin of the table. The candy column total shows 60 customers out of 200. That's 30% choosing candy overall. Pretty cool how the answer is literally sitting in the margin, right? Okay, here's where it gets really interesting. What if someone already bought soda? What's the probability they're a child? Now we're doing conditional probability. We've narrowed our world down to just soda buyers. Let's focus only on those 50 soda buyers. How many are children? 20. So out of soda buyers specifically, 40% are kids. Makes sense. Kids love their soda at the movies. Here's what blows my mind about these tables. Everything's right there in front of you. Each cell gives you joint probabilities, the margins give you marginal probabilities, and when you take ratios within rows or columns, boom, conditional probabilities. You know what's amazing? This same table structure shows up everywhere. Medical test results, marketing data, even those confusion matrices in machine learning. Master this one table and you've mastered them all.
All right, let's talk about something we all deal with, email. Your email provider has this clever system where they route messages through 3 different servers. But here's the catch. Each server has different error rates. Server A handles 50% of all emails with a 2% spam detection error. Server B handles 30% of emails, but has a higher 5% error rate. And server C, it handles 20% of emails with the lowest error rate, just 1%. So here's the million-dollar question. What's the overall probability that any random email gets incorrectly classified? This is where the law of total probability becomes your best friend. Think of it like this. An email can take one of 3 paths, and each path has its own chance of going wrong. Let me show you how this works. An email gets misclassified in 3 possible ways. It goes through server A and gets misclassified, or through server B and gets misclassified, or through server C and gets misclassified. So let's calculate each path separately. Server A handles half your emails, that's a lot, with a 2% chance of messing up. Server B handles 30% of emails, but it's less reliable with a 5% error rate. Server C only handles 20%, but it's the most accurate with just 1% errors. Now here's the magic. We multiply each server's usage by its error rate, then add them all up. When we do the math, we get a 2.7% overall error rate. Not bad. So here's what's powerful about this. Whenever you have multiple ways something can happen, just break it down. Calculate each path's probability separately, then add them all together. This same idea works for anything. Quality control in factories, medical test procedures, even figuring out why your pizza is late. The law of total probability helps you see the big picture by examining all the pieces.
Okay, this one's really important. It could literally save you from unnecessary worry someday. We're talking about medical testing and why a positive test result might not mean what you think it means. Here's our scenario. There's a rare condition that affects just 0.5% of the population. That's only 5 people out of every 1,000. We have a screening test that's pretty good, 95% sensitivity, meaning it correctly identifies 95% of people who have the condition, and 98% specificity, meaning it correctly identifies 98% of people who don't have it. Now, here's the big question. If someone tests positive, what's the probability they actually have the condition? Most people hear 95% accurate test and think, well, if I test positive, I probably have it. But that's not how the math works. Let me show you something that'll blow your mind. Let's imagine we test 10,000 people. Out of those 10,000, only 50 actually have the condition. Remember, it's rare. The other 9,950 are perfectly healthy. Now, let's run our test on everyone. Of the 50 people with the condition, about 48 will test positive. That's our 95% sensitivity at work. Great. But here's the kicker. Of the 9,950 healthy people, about 199 will also test positive. Those are false alarms, our 2% false positive rate. So let's add this up. Total positive tests, about 247 people, but only 48 of them actually have the condition. That means if you test positive, your actual chance of having the condition is only about 19%, not 95%, just 19. I know. This seems impossible. How can a 95% accurate test give you only a 19% chance? It's because the condition is so rare that even a small false positive rate creates way more false alarms than true positives. This is Bayes' rule in action. It forces us to consider not just the test accuracy, but also how common or rare the condition is. When something's really rare, even great tests produce mostly false alarms. So, here's the takeaway. If you ever get a positive test for something rare, don't panic. Ask for a follow-up test. The math is actually on your side. This is why doctors don't diagnose based on a single test. They understand that with rare conditions, most positive results are false alarms.
All right, time to put everything together. An online store sells shirts in 3 colors, and I've got some interesting data for you. Red shirts make up 40% of all sales. Blue shirts are 35%, and green shirts are 25%. But here's where it gets interesting. They all have different return rates. Red shirts get returned 10% of the time. Blue shirts, 15%, the highest. And green shirts are the winners with only 5% returns. So first question, what's the overall return rate for the store? This is the law of total probability in action. We need to consider each color's contribution to the total returns. Think about it like this. Red shirts are 40% of sales, and 10% of those get returned. Blue shirts are 35% of sales, but 15% come back. Green shirts are only 25% of sales, and they have the lowest return rate at 5%. When we calculate each color's contribution and add them all up, we get 10.5% overall return rate. Not too bad. Now here's a twist. If a shirt is returned, what's the probability it was blue? Time to flip our thinking with Bayes' rule. We're going from given the color, what's the return rate, to given it's returned, what's the color?
Remember how blue shirts had that high 15% return rate? Well, when we look at just the return shirts and do the math, exactly half of all returns are blue shirts. Even though blue shirts are only 35% of sales, they make up 50% of returns. Okay, last part. If you order 2 shirts independently, what's the probability at least one gets returned? This is where we combine independence with the complement rule. It's like a probability combo move. Each shirt has a 10.5% chance of being returned. Now, for at least one problems, here's the trick. Calculate the probability that neither gets returned first. That's easier. The chance both shirts are keepers works out to about 80%. So flip that around. If there's an 80% chance of no returns, there's a 20% chance of at least one return. Do you see what just happened? We use the law of total probability, then Bayes' rule, then independence and the complement rule, all in one real-world problem. This is exactly how probability works in practice. Different concepts working together like instruments in an orchestra. Okay, here's a situation we've all been in. Waiting for the bus. The schedule says it arrives uniformly between 8 a.m. and 8:15 a.m. That uniformly part means it's equally likely to show up at any moment in that window. First question, what's the probability it arrives before 8:05 a.m.? Now, this is different from what we've been doing. We're not counting specific outcomes anymore. We're dealing with continuous time. The bus could arrive at 8:03 and 27 seconds or 8:07 and 11.5 seconds. There are literally infinite possibilities in that 15-minute window. Check out this timeline. But here's the beautiful thing. With uniform distributions, probability is just a ratio of time intervals. We want the bus before 8:05, so that's the first 5 minutes of our 15-minute window. 5 minutes out of 15 total minutes. That's 1/3. So there's a 33% chance you'll catch that early bus. Now what if I ask, what's the probability it arrives between 8:03 and 8:10 a.m.? Same idea. Just measure the time interval. From 8:03 to 8:10 is 7 minutes. 7 minutes out of our 15-minute window gives us almost half. 47% chance the bus shows up in that range. Here's my favorite question. What's the expected arrival time? When should you expect the bus on average? For uniform distributions, this is super elegant. The expected value is always right in the middle. Take 8 a.m., add 15 minutes, divide by 2. The bus arrives at 8:07:30 on average. Some days it's early, some days it's late, but over hundreds of mornings, it averages out to exactly 8:07:30. So here's what's cool. Continuous probability uses the same logic as discrete probability. Instead of counting outcomes, you measure time. Instead of adding up cases, you calculate ratios of intervals. The fundamental idea, favorable over total, stays exactly the same.
All right, you've made it past the half mark. Most people quit by now. You're still here. You're different. And this next problem, it's gonna blow your mind. Here's the game. You roll a die repeatedly until you get a 6. Each roll costs you $1. But when you finally roll that 6, you win $10. Simple rules, deep mathematics. So here's the big question. What's the expected number of rolls you'll need? Check out this die rolling. Now, you might think we need to calculate every possible outcome. What if it takes 1 roll, 2 rolls, 3 rolls, even 100 rolls? That's impossible. But here's where recursion becomes your secret weapon. Let me show you something brilliant. Let's call the expected number of rolls E. Now watch this. We can define E in terms of itself. Think about your very first roll. You always have to roll at least once, right? Now, 2 things can happen. With probability 1/6, you roll a 6. Boom, game over. You're done in exactly 1 roll.
But with probability 5, 6, you don't get a 6. And here's the key insight. You're right back where you started. You still expect E point more rolls to get that 6. So our equation becomes E equals 1, that first roll, plus 5, 6 times E, the expected additional rolls if you fail. Let me break this down even more. That first roll always happens. If you succeed, 1/6 chance, you need 0 more rolls. If you fail, 5/6 chance, you expect E point more rolls. Now here's the magic. We solve for E. A little algebra gives us E equals 6 rolls. On average, you'll need exactly 6 attempts to roll that 6. Isn't that beautiful? The die has 6 sides, and you expect to roll it 6 times. There's a poetic symmetry there.
Okay, so what about your profit? You expect to spend $6 on rolls, but you win $10 when you succeed. That's an expected profit of $4. So should you play this game? Absolutely. This game has positive expected value. You're expected to win money. Check out this comparison. Most casino games, the house has the edge. Negative expected value. You lose money long term. But this game, you have the edge. $4 expected profit per game. But wait, here's the reality check about variance. Look at this spread. Yes, you expect $4 profit, but individual games? Total chaos. Get lucky and roll a 6 immediately? $9 profit. Get unlucky and need 15 rolls? $5 loss. Expected value is your long-term compass. Play this game 1,000 times, you'll be around $4,000 richer. Play it once? Who knows? That's both the beauty and the brutality of probability. Expected value tells you what's smart in the long run, but in the short run, anything can happen. The math says play, but make sure you can handle the swings. Picture this. You and your friend walk into a sushi restaurant. They offer simple 2-piece orders, salmon, tuna, or eel. You both decide to order randomly. Maybe you're feeling adventurous. So first question, what's the probability you both end up ordering salmon? Well, let's think about this systematically. Each of you has 3 choices and you're both ordering. How many total ways can this play out? Check out this systematic listing. Think of it like a grid. You've got 3 choices, your friend's got 3 choices. That gives us 3 times 3 equals 9 total possible outcomes. And in only one of those outcomes, do you both order salmon? So the probability, 1 out of 9. About 11%. Not very likely you'll accidentally match on salmon. But wait, here's something cool. Since you and your friend order independently, you're not influencing each other, we can use a shortcut. The probability you order salmon is 1/3. The probability your friend orders salmon is 1/3. Multiply them together, 1/3 times 1/3 equals 1/9. Same answer. Now here's where it gets interesting. Suppose the waiter comes by and says, I see at least one of you ordered salmon. Given this new information, what's the probability you both ordered salmon? This changes everything. We now have conditional probability. We're working with new information. Let's think about it. Out of our 9 possible outcomes, which ones have at least one salmon order? Let me count. There are actually 5 outcomes where at least one person gets salmon. And of those 5, only one has both people ordering salmon. So now the probability jumps to 1 out of 5. That's 20%, almost double what it was before. Isn't that fascinating? Just knowing that at least one person ordered salmon nearly doubles the chance that both did. Here's the big lesson. Independence is your friend in probability. When events don't influence each other, you can just multiply their individual probabilities. It's like having a superpower that turns complicated problems into simple multiplication. Anytime you can break a problem into independent pieces, do it. All right, gamers, let's talk about something you've probably experienced. Loot boxes. Here's how this particular game works.
Each box contains exactly one item. 70% of the time, you get a common item worth $1. 25% chance of a rare worth $5. And that ultra-rare legendary? 5% chance, but it's worth $50. Oh, and each box costs $3 to open. So here's the million-dollar question. Is it worth it? Time to calculate expected value. This tells us what we'd win on average if we opened thousands of boxes. Check out this loot box animation. We need to weight each prize by how often it appears. Commons show up 70% of the time but are only worth $1. That contributes 70 cents to our average. Rares appear 25% of the time at $5 each. That adds $1.25. And those legendaries? 5% time at $50 adds $2.50. Add it all up, 70 cents plus 125 plus 250 equals $4.45 average value. But remember, the box costs $3. So your expected profit is $4.45 minus 3, $1.45. The game is actually in your favor. But wait, before you start buying boxes, let me show you something. What's the probability of not getting a legendary in 10 boxes? This is where reality hits hard. Let's use the complement rule. It's easier to calculate no legendaries than to figure out all the ways to get one or more. Each box has a 95% chance of no legendary. Since boxes are independent, we multiply. 0.95 to the 10th power. 59.9%. Even after spending $30 on 10 boxes, you're more likely to get 0 legendaries than to get even one. Feel that frustration? That's by design. Okay, here's a brain teaser. If you open exactly 3 boxes and get exactly 1 legendary, how many different ways could that happen? Think about it. The legendary could be in the first box, the second box, or the third box. That's 3 different sequences. In math terms, we're choosing which one of 3 positions gets the legendary. So here's the dark psychology of loot boxes. Yes, they might have positive expected value. Yes, you'd profit in the long run. But those legendary items? They're engineered to be just rare enough to keep you hooked. The math says you'll win eventually, but eventually might be expensive. Remember, expected value is about the long run. In the short run, the house uses variance to keep you playing.
You know what? The casual learners quit a while ago. But you're still here. You're different. And this next problem shows how probability appears in everyday business decisions. Here's the setup. A coffee shop tracks when customers arrive and what they order. Customers arrive uniformly between 7 and 9 a.m. The early birds, before 8 a.m., love their coffee. 80% order it. But the later crowd, only 60% want coffee. So first question, what's the overall probability a random customer orders coffee? This is beautiful. We're combining continuous probability with the law of total probability. Check out this timeline. Arrival time is continuous and uniform over 2 hours. That means exactly half arrive before 8 a.m., half arrive after. Perfect 50-50 split. Now, we use the law of total probability. We've got 2 paths to coffee. Early arrivals, who order coffee, plus late arrivals, who order coffee. Let's calculate. Early arrivals, 50% of customers, 80% want coffee. That's 0.5 times 0.8 equals 0.4. Late arrivals, 50% of customers, 60% want coffee. That's 0.5 times 0.6 equals 0.3. Add them up, 40% plus 30% equals 70% of all customers order coffee.
Now here's where it gets clever. If someone orders coffee, what's the probability they arrived before 8 a.m.? We're flipping the question. Instead of given the time, what do they order? We're asking, given the order, when did they arrive? This is Bayes' rule territory. Think about it. The vitamy, there's halal or the 50% half too, several in the time. There's total push-ups. Before we see any order, there's a 50-50 chance someone arrived early. But coffee is more popular with early birds, 80% versus 60%. When we crunch the numbers with Bayes' rule, that coffee order bumps the probability up to 57%. The coffee order is evidence. Not super strong evidence, but evidence, nonetheless, that they're an early customer. Last question. What's the expected arrival time for a random customer? This one's actually super easy. With uniform distributions, the expected value is always the midpoint. Customers arrive uniformly between 7 and 9 a.m., so the average arrival time is exactly 8 a.m. Right in the middle. What I love about this problem is how it mixes continuous and discrete probabilities seamlessly. Time is continuous, coffee choice is discrete, but the probability rules connect everything together. This is exactly the kind of analysis real businesses do every day.
All right. Here's a scenario every programmer knows. The dreaded technical interview. You're randomly assigned 2 coding problems from a bank of 10. Here's the breakdown. 4 easy problems, 4 medium, and 2 hard ones. Your success rates? 90% on easy problems, 60% on medium, and just 30% on those brutal hard ones. Let's start with this. How many different problem sets could you possibly get? This is a combinations problem. And here's the key insight. Order doesn't matter. Getting problem number 1 and then problem number 5 is the same as getting problem number 5 and then problem number 1. You're just solving 2 problems. Check out this combination formula. We need 1 choose 2. That's all the ways to pick 2 problems from 10. When we work it out, 10 times 9 divided by 2, that's 45 different possible problem sets. Now here's where it gets really interesting. Suppose you just crush the interview, solve both problems perfectly. Given that stellar performance, what's the probability both problems were easy? This is where most people's intuition goes wrong. You might think, I solved them both easily, so they were probably easy problems. But let's see what Bayes' rule says. We need to think about this backwards. Let me break it down step by step. First, what's the chance of getting 2 easy problems? Out of 10 problems, 4 are easy. So the ways to pick 2 easy problems, that's 6 out of 45 possible sets. Second, if you did get 2 easy problems, what's the chance you'd solve both? That's 90% times 90% equals 81%. But here's the tricky part. We need to consider all the ways you could solve both problems. Maybe you got 2 easy ones. Maybe 1 easy and 1 medium. Maybe you got lucky with hard problems. Let me calculate each scenario. 2 easy problems, 1 easy and 1 medium, 2 medium problems, and so on. When we add up all the ways to solve both problems, we get about 43%. Now for the shocking conclusion. Using Bayes' rule, if you solve both problems, the probability they were both easy is only 25%. Wait, what? You crushed the interview, but there's only a 1 in 4 chance both problems were easy? That's right. Your success could mean easy problems, or it could mean you're just that good. The math doesn't lie. Perfect performance doesn't necessarily mean easy questions.
The last question, on average, how many problems do you expect to solve? This is where we combine everything we know. We need to consider all possible problem combinations and their solving probabilities. Think about it this way. If you get 2 easy problems, you'll solve 90% of each. So that's 1.8 problems on average. If you get 1 easy and 1 medium, that's 90% plus 60%. 1.5 problems solved. Let me work through each scenario. Check out this table showing all the possibilities. When we weight each outcome by its probability, 2 easy problems happen 6 out of 45 times and gives us 1.8 solved.
One easy and one medium happens 16 out of 45 times and gives us 1.5 solved. Keep going through all combinations. The final answer? You expect to solve about 1.32 problems on average. That's right, even though you're a coding wizard who crushes easy problems 90% of the time, the mix of difficulties brings your average down to just over one problem solved. Here's the beautiful insight. This number, 1.32, perfectly captures the challenge of technical interviews. It's not just about your skill level. It's about the luck of the draw, the problem difficulty distribution, and how those interact with your abilities. And now, you can calculate exactly what to expect.
Let's analyze some real pizza shop data. Here's what we know. 60% of orders are large pizzas. 40% of orders include drinks, and 25% are both large pizzas with drinks. Oh, and delivery takes uniformly between 20 and 40 minutes. First question. Are ordering a large pizza and including drinks independent events? Here's how we test for independence. If two events are truly independent, then the probability of both happening should equal the probability of the first times the probability of the second. Let's check. If these were independent, we'd expect 60% large pizza times 40% drinks equals 24% should order both. But our data shows 25% actually order both. That's slightly higher than expected. So they're not independent. Large pizza customers are slightly more likely to add drinks to their order. Makes sense, right? Bigger pizza probably means more people eating, which means more drinks. Next question. What percent of orders include either large pizza or drinks, or both? Time for the addition rule. Remember, we can't just add 60 plus 40 because some orders have both. We'd be double counting. So it's 60% large pizza plus 40% drinks minus 25% both equals 75%. 3 out of 4 orders have at least one of these profitable add-ons. Now here's an interesting one. If someone orders a large pizza, what's the probability their delivery arrives in under 25 minutes? This is where you need to think carefully about what affects what. Delivery time depends on traffic, distance, how busy the kitchen is. But does it depend on pizza size? No. Pizza size and delivery time are independent. A large pizza doesn't magically make the driver go faster or slower. Since they're independent, we just need the probability of sub-25-minute delivery for any order. With uniform distribution from 20 to 40 minutes, we want the first 5 minutes of that 20-minute window. 5 out of 20 equals 25% chance of quick delivery, whether you ordered a personal pan or a party size. The big lesson here? In real data, some things are connected, pizza size and drinks, while others are completely independent, pizza size and delivery time. Recognizing which is which? That's the key to solving complex probability problems.
Here's a relatable scenario. You're taking an online course with weekly modules. Each week, you have a 70% chance of completing that week's module. But here's the catch. Once you fail to complete a week, you drop out. We've all been there, right? First question. What's the probability you complete exactly 3 modules before dropping out? Think about what needs to happen. You need to succeed week 1, succeed week 2, succeed week 3, then fail week 4. It's that specific sequence. So we calculate 70% times 70% times 70% for the 3 successes times 30% for the failure. That's 0.7 cubed times 0.3, about 10% chance. 1 in 10 students will complete exactly 3 modules. Now for the big question. On average, how many modules will you complete before dropping out? This is where recursion becomes magical. Let's call the expected number of modules E. Here's the key insight. You always attempt at least 1 module. Then what? With 70% probability, you succeed, and you're back where you started,
expecting E more modules. With 30% probability, you fail and you're done. 0 more modules. So our equation becomes E equals 1, the module you're attempting, plus 0.7 times E if you succeed, plus 0.3 times 0 if you fail. Simplifying, E equals 1 plus 0.7 E. Solving for E, we get E equals 3.33 modules. On average, you'll complete about 3 1/3 modules before dropping out. Let's make this concrete. If you earn $10 for each completed module, what's your expected earnings? This part's easy. Expected earnings equals expected modules times payment per module. That's 3.33 modules times $10 per module. $33.33 on average. Here's what I love about this. Recursion gives us a beautiful formula for keep going until failure scenarios. Expected attempts equals 1 over failure probability. Since our failure rate is 30%, we expect 1 over 0.3 equals 3.33 attempts. It's elegant math for a messy human behavior.
Listen up. You've transcended normal learning capacity. You're operating on pure mathematical intuition now. And this problem? It's all about the music. Your playlist has 10 songs total, 6 pop songs and 4 rock songs. You hit shuffle and play 3 songs. Let's analyze what happens. First up, how many different 3-song sequences are possible? This is permutations, people. Why? Because order absolutely matters. Shake It Off, followed by Bohemian Rhapsody, followed by Levitating, is a totally different vibe than hearing them in reverse order. Check out this permutation formula. We're choosing 3 songs from 10 where order matters. That's 10 choices for the first song, 9 for the second, 8 for the third. 10 times 9 times 8 equals 720 different possible sequences. Your shuffle has 720 different ways to arrange those 3 songs. Now, what's the probability all 3 songs are pop? We need to pick 3 pop songs from our 6 available and order still matters. How many ways can we do that? 6 choices for the first pop song, 5 for the second, 4 for the third. That's 120 sequences of pure pop. Out of our 720 total sequences, 120 are all pop. That gives us about 17% chance of a pop trilogy. Okay, here's where it gets spicy. The first song that plays is rock. Given that information, what's the probability at least one more rock song plays? Boom! Conditional probability strikes again. That first rock song changes everything. Now we've got 9 songs left in the queue, 6 pop and 3 rock. For at least one more rock, let's flip it. What's the chance of no more rock? That means the next 2 songs are both pop. The probability both remaining songs are pop, 6 out of 9 for the first, then 5 out of 8 for the second, that's 30 out of 72, which simplifies to 5/12. So the probability of at least one more rock song, 1 minus 5/12 equals 7/12, about 58%. Here's what's beautiful. That first rock song completely changed our probability landscape. We went from a 40% rock playlist to a 58% chance of more rock. Conditional probability doesn't just update numbers, it transforms the entire sample space.
This is it. You've reached the summit. 20 problems deep, and you're still here. This is what mathematical mastery feels like. We've got 100 restaurant reviews to analyze, sorted by rating and meal type. This final problem brings everything together. Check out this table. We're looking at lunch versus dinner and ratings from 5 stars down to 3 or fewer. Every cell tells a story about customer satisfaction. First question. If someone had dinner, what's the probability they gave 5 stars? This is pure conditional probability. We're narrowing our focus to just dinner customers. Out of 55 dinner customers total, 25 gave 5 stars. That's 25 out of 55. About 46%, nearly half of dinner customers are leaving 5-star reviews. The dinner service is killing it. Now let's flip the script. If someone didn't give 5 stars, what's the probability they had lunch? We're conditioning on a different event now. First, how many reviews aren't 5 stars? 100 total minus 40 5-star reviews equals 60 reviews. Of those 60 non-5-star reviews, how many were lunch? Let me check. 30. 30 out of 60. Exactly 50%. Half the disappointed customers were lunch crowd. Final question, and this one ties everything together. Are meal type and rating independent? Remember, for independence, the probability of both events must equal the product of their individual probabilities. Let's test it. The probability of 5 stars and dinner, 25 out of 100. That's 25%. If they were independent, what would we expect? Probability of 5 stars, 40%, times probability of dinner, 55%, equals 22%. But we actually observed 25%. They're not independent. Dinner customers are more likely to give 5 stars than pure chance would suggest. You just completed something 95% of people won't. Your brain has been transformed. But here's the truth. This isn't the end. Your brain needs repetition to make this permanent. Do this again in a week, then again in a month. That's when it truly sticks. The foundation you just built, every high-paying tech career, data science, AI engineering, quantitative finance, machine learning. You now have the rare understanding that separates beginners from the truly capable. You're not bad at probability, you just hadn't been taught this way. You were never bad at math. Today proved it. Stay psycho-focused.